Okay, we're going to third screencast, talking about collision theory. There are a lot of objectives to be met in the screencast, some of which you should already be familiar with. Talking about, first thing here, kinetic theory, kinetic molecular theory, movement of particles, and that average energy of those particles is proportional to absolute temperature, which means we're talking about Kelvin. Define the term activation energy, describe collision theory, predict and explain using collision theory the qualitative effects of particle size, temperature, concentration, and pressure on the rate of a reaction. We're going to learn about Maxwell-Boltzmann energy distribution curves for a fixed amount of gas at different temperatures, and its consequences for changes in reaction rate, how those two things relate. Describe what effect a catalyst has on a chemical reaction, and again, Boltzmann curves for reactions with and without catalysts. Okay, so let's begin with the collision model. In a chemical reaction, bonds are broken, new bonds are formed. Please remember that it always takes energy to break a bond. It is always an endothermic change. New bonds formed, energy is released. Okay. These two things taken together determine whether the overall chemical reaction is exothermic or endothermic. Okay. Back to the collision model. Molecules can only react if they collide with each other. If they never make contact, they can't break bonds and make bonds. Okay. Furthermore, when molecules combine, they actually have to combine with the correct orientation, sometimes called with the correct geometry, and with enough energy to cause that bond breakage and then the subsequent formation. So you can see these two particles before the collision, they collide exactly with the right orientation, and then after collision there's a bond broken, and they make new substances. So pretty much three things. They have to collide. They have to collide with the correct orientation, and they have to collide with enough energy. Three things for them for a reaction to actually happen. Let's talk about activation energy. There's a minimum amount of energy that is required for a reaction to start. Okay, if I had a sample of oxygen and hydrogen, they can coexist for a long time with not ever reacting. But if I introduce a spark to that system, I will have quite the explosion. That spark, okay, is called the activation energy, and it's a lot like a golfer. You know, when you're playing miniature golf and you have to get to that the hole-in-one, you have to make sure you hit the ball hard enough so it makes it over that hill. This little part here is referred to as the energy necessary for the progress to proceed. It's actually called the activation energy. And if we look at a reaction coordinate diagram, this takes a step-by-step through the reaction for methyl isonitrile. I probably didn't say that right, excuse me. Alright, so anyway, I have the reactants here. Okay, I'm increasing the energy of the system, right? And you can see that this molecule is changing till I get to the peak here, and that's where I have something called the activated complex. It is the most highest energy form for this molecule, and you see this bond is kind of flipping. Okay, and then it all goes downhill, and then I finally make my products at the end. This difference in energy is called the activation energy, has a symbol of E with a subscript A. You should be familiar with the difference in energy between the reactants and the products. Okay, internal energy is really specifically what it is, but for our systems it's the same as enthalpy. And remember that the x-axis here is the reaction pathway, and then energy on the y-axis. Okay. Again, the highest point is named its activation complex or the transition state. Okay, we covered all that. So, if we look at these series of equations, they're not equations, they're graphs, and we're asked to rank the reactions from the slowest to the fastest, assuming that they have nearly the same frequency factors. Frequency factors mean the same orientation requirements and the same collision requirements. So if we rank them slowest to fastest, really what we're comparing is the activation energy. Here is the activation energy for the first graph, the activation energy for the second graph, and the activation energy for the third graph. Okay. The fastest would be 1, so I'm ranking from slowest to fastest, so 1 is going to be faster than 3, then 2. I'm not sure they're less than, this should be backwards, because the time, they're greater. Or I could have just said 2, 3, 1. Okay. The idea is the lower the activation energy, typically the faster the speed of the reaction. So again, 1 would be the fastest, 2 would be the slowest, and it's related to the activation energy. Now let's take a look at Maxwell-Boltzmann distributions and find out why activation energy and temperature has something to do with reaction rates. If you remember back from energetics, kinetic molecular theory, that temperature is defined as the measure of the average kinetic energy of the molecules in a sample. And we look at a graph, we have the fraction of molecules on the y-axis and kinetic energy on the x-axis. This blue curve represents a lower temperature, okay, with the average being lower kinetic energy for the peak than that higher in red. And if we notice, if I draw a graph or a line saying that this is the minimum energy needed for the reaction to proceed, meaning the activation energy, if you compare the lower temperature curve with the higher temperature curve, you can see that there are more molecules at the higher temperature that have sufficient energy for the reaction to proceed. Okay, so at higher temperatures, the reaction rate should be a little larger. At any temperature, there is a wide distribution of kinetic energy. As the temperature increases, it broadens and flattens. Okay, and then, like I said before, at higher temperature, there's a larger population of molecules that have a higher energy. So how do we increase the rate of a chemical reaction? Well, we could increase the surface area of the solids, increase the temperature as we just saw, shine a light for certain reactions, add a catalyst, increase the pressure of gases, or increase the concentration of the reactants. So increasing the surface area. When you increase the surface area, you increase the chances of collisions. More collisions, higher the rate. We already talked about the Maxwell-Boltzmann distribution of molecular energy. Okay. And increasing the temperature alters the distribution. The area under the curve stays constant because that is related, that is just the total number of particles. And then we talked about the lower temperature having a lower average molecular energy, higher temperature, higher average kinetic energy with more of the particles at the higher end having the energy up here. Draw that line with the activation energy. Okay, and you'll see at the higher temperature you have more particles underneath the curve with the higher energy. Shining a light, this is only certain reactions. Okay. UV light sometimes will provide enough energy to break the bond and initiate a reaction, and then the greater the intensity of that light, the greater the effect. Okay, and then you can see a process. What happens when we add a catalyst? A catalyst actually speeds up a reaction by providing an alternate pathway for the reaction that has a lower activation energy. And just like we saw that 3 graphs looking at the activation energy, if you lower the activation energy, more particles have enough energy to overcome that energy barrier. And if you look at a graph looking at the activation energy without a catalyst, and then if you look at one with the catalyst, this green line, you can see that the activation energy is lower, so that more particles, remembering the Boltzmann distribution graph, more particles would have that energy, and you will increase the rate. So remember that just by adding that catalyst, we're shifting that activation energy over. We're not doing a different distribution in the Maxwell-Boltzmann, but we're shifting that energy lower so that more particles are under the curve and able to initiate the reaction. Important thing to know about catalysts is that you have something called homogeneous catalysts. These are going to be in the same phase as the reactants. Okay, and then you have heterogeneous catalysts. That's a different phase. This is usually a solid in either a liquid or a gas type of reaction. Okay. Catalysts remain chemically unchanged at the end of the reaction. You avoid the need to supply extra heat by shifting that activation energy lower. Excuse me. Okay, and things to remember for the next unit, which will be equilibrium, is that catalysts do not affect the position of the equilibrium. They just affect how fast you will get to that equilibrium. Here's a picture of a way a catalyst can work. They hold the reactants together, and that speeds up the reaction. Enzymes are an example of catalyst in a biological system. Okay. And of course, increasing the concentration of a component is going to speed up the reaction by providing more frequent collisions. Okay, increase the rate of reaction. Increasing the pressure for a gas system forces those gases closer together, increasing the number of collisions and increasing the rate.